Welcome to qnawire.
Problem 7.35 is about a model for the potential energy function between two atoms in a diatomic molecule. This is called the Lennard-Jones potential. It's pretty commonly used for modeling how diatomic molecules work. And we want to find a bunch of things out about this. So what is the force as a function of the distance, first of all? And when we want to sketch the graphs of the force and the potential energy, we want to find the equilibrium disk separation R Wait a minute. Oh, I'm sorry. This is part of part A. So let's just ignore the B here. Anyway, the equilibrium distance, and just determine whether it's a stable or unstable equilibrium. Assuming that the molecules are at the separation of our equilibrium, we want to know what the dissociation energy is, which is the energy that must be added to the system in order to get them to be freed from each other. And then we're told some information about carbon dioxide, and we want to find what are the values of A and B for that. So, the force is going to be entirely in the radial direction. It's going to be the negative derivative of the potential energy. So we see here this is r to the negative 12th. So we'll have a negative and then another negative. And so this will be 12a over r to the 13th. And then this will have a negative sign here. We'll get a negative 6 out. And then we'll get another negative sign, so it's negative again. This will be 6b over r to the 7th. And so if we sketch these, U, it has a vertical asymptote of the y-axis. It dips down to be negative and then is negative with a horizontal asymptote out to infinity here. And here at the bottom of the potential well will be the equilibrium R. And then the force graph will look similar, except the equilibrium is here where the slope of this is 0. So force is 0 here. And we can see that because the force is pushing them apart when they're closer together than the equilibrium, and it's pulling them together when they're further apart, that this is a stable equilibrium. So now, for part B, we want to find this equilibrium. And so we know it's at the minimum of the potential energy. And, you know, to do a minimization problem, you take the derivative, set it equal to 0, and we've just computed the derivative. So it's also where the force is equal to 0. So we see that it's 12a over r to the 13th is going to be equal to 6b divided by r to the 7th and solving this, we see the equilibrium distance is 2a over b, and it's the 6th root of that. So, start up a new page here. We want to find this dissociation energy starting from R equals our equilibrium that we found. It's 2a over b to the 1/6. The potential energy at equilibrium R, just put this into our expression and evaluate it and simplify it, is negative b squared over 4a. So we draw the potential energy again. In order to separate the two atoms, we have to get them slightly, the energy has to be slightly above what's required to get past the maximum value of the energy as the distance increases to infinity, which, because the maximum value it has as r goes to infinity is 0, we just need to add enough energy to be the negative of this, basically. So we increase the energy by this much, and they'll be able to go apart to an infinitely far distance away without being reattracted to each other. And that's what it means for something to dissociate, or in the case of like gravitation, if you want something to be able to escape the gravitational influence of another body, like if you wanted to get a rocket off of Earth and then go arbitrarily far away from it, there's the escape velocity. That's the same sort of thing, where you have to add at least as much energy as the potential energy it has sitting on the surface of the Earth. Anyway, so the dissociation energy is just b squared over 4a. So now for part D, we're told a few things about the carbon monoxide molecule, namely that its equilibrium separation is 1.13 times 10 to the negative 10th meters, and the dissociation energy is 1.54 times 10 to the negative 18th joules. So now I want to find what A and B are. So we know an expression for RE and an expression for ED. So we can just go ahead and solve those for A and B. 2A over B to the 1/6. Dissociation energy B squared over 4A. So, BRE to the 6th equals 2A. Or a BD equals B squared. And so we can solve one of these for A, put it into here, or into the other one, find B, and then put that into the other equation. And you end up finding that B is equal to 6.41 times 10 to the negative 78 joule meters to the 6th. And then back substituting that in, you can find that A is equal to 6.67 times 10 to the negative 138 joule meters to the 12th. And so you can see from all of the exponents here that atomic and molecular physics happens at a much smaller scale than the sort of roughly human scale that the SI units were, designed for, which, you would expect because atoms are incredibly tiny. So don't be disturbed by how small these are. It's because atoms are a lot smaller than, like a human is a couple meters tall and so forth. So that's why the numbers end up crazy.